Hello, and in the continuation of our discussion on parallel lines, let's also talk about convex polygon. We define a polygon as a closed plane figure whose sides are line segments that intersect only at the endpoints. I would like to note here that it should be a closed plane figure. Okay, it should be a polygon should be a closed plane figure, and that the sides are line segments, and that they only intersect at the endpoints, meaning to say that it's vertices. Okay. Okay, now in our example here, based on our definitions of polygons, again, we define a polygon as a closed plane figure whose sides are line segments that intersect only at the endpoints. So basically, we say that in the first, let's say this one is A, we can say that this is not a polygon because not a polygon. Okay, because notice that even though RT and RS are segments, ST is not a segment but a curve. Okay, ST is a curve. For B, notice as well that even though WX, XY, and YZ are segments, it it's still not a polygon. Okay, not a polygon, because we basically define that it should be closed. Okay, because it is not closed. Okay, and WZ are not connected. Okay, and for letter C, we know that this is not a polygon because there are no segments. Okay, there are no segments. Okay, so if you see these things, if even though they seems to be a polygon, particularly letter A and letter B, because they do have some properties of what polygons are, but unfortunately they are not. Okay. However, if we talk about if a shape is a polygon, we can actually classify them. Okay, there are two classifications of polygons, which are convex polygon and concave polygon. So a convex polygon, just like our figure here, is a closed shape. It's a closed shape where none of the vertices are pointed inward. Meaning to say that when a line crosses the convex polygon, it intersects at most the two sides of the polygon. Okay, so if we are to draw a line between two uh, opposite, okay, two opposite vertices of that polygon, then it should be inside. Okay, just like this one. If we are to draw a line segment from this point up to this point, then let's say from this point up to this point, and then let's say from this point up to this point, okay, as well as this, if we are to draw a line segment connecting from this point up to this point, from this point up to this point, okay, that's what we call convex polygon. And the angle measures of convex polygons are between 0 degrees and 180 degrees. On the other hand, we have concave polygons. A concave polygon is a polygon that is not convex, of course, and if any of the diagonals of a polygon are formed partly or fully outside the polygon, then it is called concave. So say for example, if we are to connect this point up to this point, so this point up to this point, from this point up to this point, okay, they are called concave polygons. Okay, now so let's talk about the classifications of polygons according to the number of sides. Okay, basically, if we can recall your plane determination postulate, so your plane determination postulate says that suggests that the minimum number of points to determine a plane is 3. So basically, that is a triangle. Okay, so triangle. You have here a polygon with 3 sides is triangle. A polygon with 4 sides is quadrilateral. A polygon with 5 sides is pentagon. 6 sides is hexagon. 7 heptagon. 8 is octagon. 9 is nonagon. 10 is decagon. And you will notice that the prefix tells you the number. Okay? Hepta is 7. Octa is 8. Nona and deca. Okay? So say for example, if we are to extend a polygon with 11 sides, so it's actually called un decagon. Okay? Un means uno. Okay? Uno. And 12 from the Spanish word dos, which is dodecagon. Okay? And if we are to reach n number of sides, that is what we call n-gon. Okay? So, say for example, a polygon with let's say 25 sides is called 25 gon. Okay? A polygon with let's say 85 sides, then it's called 85 gon. Okay? Now, a diagonal of a polygon is a line segment that joins two non-consecutive, okay, two non-consecutive, and if I may add, non-adjacent. Okay, non-consecutive and non-adjacent vertices. So if we are to use the given figure, then we can say that AE, segment AE, okay, segment AD, and segment AC are the diagonals of what kind of polygon? Okay, so we can see here that there are 7 vertices and 7 sides. So therefore, we can say that this one is a heptagon. So the diagonal of heptagon, let's name this A, B, C, D, E, F, G. Okay. Next, so given that we have a triangle with 3 sides, then we can say that it has no diagonals. Okay, because basically we define a diagonal that as a line segment joining two non-consecutive or non-adjacent vertices. So in this case, a triangle has none of it. Okay, it does not satisfy our definition. So definitely, it has no diagonals. For a quadrilateral with a quadrilateral, we know that it has 4 sides. Then it satisfies our definition. Okay, it contains non-adjacent and non-consecutive sides. Therefore, we can construct 2 diagonals. For a pentagon with 5 sides, then we can construct 5 diagonals. And for hexagon, we can construct 9 diagonals. Okay? The question is, how are we going to construct the diagonal, or how many diagonals can be found in, let's say, um, decagon? And we know that decagon has 10 sides, and a 25-gon polygon, a 100-gon polygon, an n-gon. Okay, so we're going to use a formula to determine the number of diagonals that can be found in a polygon except a triangle. Okay, so by using this theorem, our theorem is the total number of diagonals D in a polygon of n number of sides, that is n-gon, is given by the formula D is equal to n times n minus 3 all over 2. Okay, actually we can prove this by using the concept of combination. Okay, and we need to do is to make the diagonals, we need to choose the number of pairs of 2 vertices that can be formed from uh, the n number of vertices. Okay, and that is let's have the diagonal. The diagonal can be determined by um, the number of pairs of 2 vertices, and that's a combination. So a combination in your first year mathematics under statistics and probability, the combination of n given 2 at a time. Okay, the combination of n, because we don't know the number of this is the number of sides, and 2 is the number of vertices. Okay, 2 non-adjacent vertices. Okay, and we subtract this one by the n number of sides, which is basically, if we are to write the combination of 2 of n chosen or given 2 at a time, then we have n factorial divided by 2 minus n. And basically, we define n factorial as n times n minus 1. Okay, and if we are to expand n factorial divided by 2, okay, then minus n. Now if we are to simplify this expression, then what we have here is the least common multiple of the denominator is 2. Then what we have here is n times n minus 1 all over 2 minus, this is 2 divided by 1, the denominator is 1, 2 divided by 1 is 1 times n is 2n. Okay, and that we already have similar fractions. And then simplifying our similar fractions, we have, okay, simplify first our expression in the numerator. What we have there is n squared, okay, minus n, and then minus 2n. I'm going to simplify it now because they have the same denominator, and this simplifies 2n squared minus 3n, okay, divided by 2. And notice that there is a common factor, which is n, and that is n times n minus 3 all over 2. And we're able to show that the theorem holds. Okay, why do we need to subtract n? Okay, because the adjacent vertices cannot make a diagonal. That's why there is minus n in our derivation. Okay, so in the next video, we're going to apply this theorem by showing you some examples.